For decades, satellites have been silent observers in the skies, capturing images critical to national security. But as global threats evolve, so too must our tools. Today, traditional reconnaissance satellites face a glaring limitation. They can only see the world in 2 dimensions. In an era where depth and detail are crucial, yesterday's technology is no longer enough. The United States Armed Forces and intelligence agencies are calling for a new standard. They require systems capable of creating accurate 3D models of strategic targets, military installations, oil refineries, weapons depots, anywhere in Earth's northeastern quadrant. These models are not just technical achievements. They are life-saving tools that improve decision-making, protect military assets, and safeguard personnel on the ground. Our sponsor, L3 Harris, aims to fill this gap with a new constellation of satellites. To be feasible, the proposed constellation must have between 3 and 12 satellites, capable of fully imaging at least 15 targets in 30 days. The images produced must have a resolution of better than 30 meters per pixel, with a field of view of 10 degrees, or a sensor half angle of 5. The constellation must have a lifespan of at least 10 years. Finally, when presented with multiple targets in a possible field of view, the satellite must be able to determine which target to prioritize. The solution to this? Versatile Exploration Capture of Targeted Object Rendering, or VECTOR.
Introducing VECTOR, a revolutionary reconnaissance satellite that features multiple advanced subsystems, including an attitude determination and control system, communication subsystem, propulsion subsystem, thermal management subsystem, a power subsystem, and most importantly, a payload. Each subsystem was designed around specific system requirements. ADCS ensures precise alignment, meeting the requirement for 0.01 degree pointing accuracy, essential for capturing images from all required angles. The communication subsystem enables reliable data transfer, using S-band for uplink and X-band for a high-speed downlink to transmit all data within a 30-day time frame. The propulsion subsystem is designed for orbital maintenance and debris avoidance requirements, with a hydrogen thruster providing a delta-V budget of 300 meters per second for adjustments and safe deorbiting. Each satellite is powered continuously with a gallium arsenide solar panel and lithium-ion batteries, maintaining energy flow during both sunlight and eclipse. The thermal subsystem regulates temperatures, keeping all satellite components within operational ranges, despite the harsh environment of space. Finally, the structure and launch subsystem is built to withstand launch stresses while adhering to the mass and size limits of the launch vehicle. Most importantly, the payload features the SpaceView 42 imager, produced by our sponsor, L3 Harris, which was chosen for its compact design, impressive resolution, and versatility, making it an ideal choice for the mission's imaging requirements. With a novel image processing technique called pan-sharpening, we can achieve high-quality, colored, and low-lit images without sacrificing resolution. This process merges our high-precision panchromatic images with 4-band multispectral data, resulting in high-fidelity, full-color imagery. The outcome is an impressive spatial resolution of 1.7 meters, combining detail and color accuracy in every image. These subsystems integrate seamlessly to ensure VECTOR meets its mission requirements with precision and reliability. Designed to overcome the limitations of current systems, VECTOR is a satellite constellation engineered to deliver high-resolution images from 288 angles, capturing over a global distribution of targets in just 30 days, providing the capability to transform fragmented images into cohesive 3D models. VECTOR gives America and her allies valuable information needed to keep protecting our national interests. This innovation sets a new benchmark for satellite reconnaissance, paving the way for smarter, safer decisions in the missions that matter the most.
The challenge of designing an optimal satellite constellation is like walking on a balance beam. On one side is the constellation's time to image. How quickly can we capture the necessary data? On the other side is the cost, a factor that can't be ignored in real-world applications. The goal? To find the sweet spot, the knee in the curve, where performance and cost achieve their perfect balance. At the heart of VECTOR's design lies a robust model. Using advanced simulations such as the ANSYS System Toolkit, also known as SDK, and optimization techniques, we ensured that every design decision was data-driven and validated. The model integrates orbital mechanics, imaging efficiency, and communication performance to deliver a constellation optimized for fast imaging times and cost effectiveness.
Since the goal is to utilize the captured images for 3D rendering, there are certain angles of the target that need to be captured by the satellite constellation. In our algorithm and SDK simulations, this translates to a certain angle bin that need to be acquired in order for a satellite constellation to be considered successful. These angles will cover elevations from 10 to 90 degrees elevation and azimuths from all 360 degrees per target. Having a 10-degree step size for each target gives a total of 288 bins that need to be achieved for 100% coverage.
Central to our design process was a genetic algorithm, purpose-built to identify the knee in the performance cost curve. The algorithm begins with a population of potential configurations of the constellation, each representing different numbers of satellites, orbital parameters, and imaging schedules. Iterating over generations of solutions, the algorithm evaluates the configuration against two primary objectives: minimizing the time to image and reducing mission cost. Fitness functions were applied, which included the simulation and data evaluation. Then scoring was applied to each solution based on the time and budget. The crossover and mutation steps introduced variations, ensuring that the search space was thoroughly explored. Once completed, the generation is populated with these new solutions. This process will reiterate until the algorithm converges on a new solution. However, a problem arises when a satellite has the opportunity to image multiple targets in one given instance. This issue is addressed by the deconfliction algorithm, a genetic algorithm that finds the optimal mission path to minimize the time to image all targets. The algorithm also accounts for the satellite's ability to orient itself and only includes solutions that are feasible given the satellite's hardware constraints.
For a 15-target scenario, the genetic algorithm-based optimizer was able to explore a design space using a population of 20 solutions for 10 iterations. 43 of the 200 solutions were feasible designs, meaning they achieved 100% image coverage. From the set of feasible solutions, a Pareto frontier was defined, highlighting the best constellation designs in terms of both cost and performance. From the Pareto frontier, the most cost-efficient and best-performing solutions can be analyzed. For the cost-efficient solution, the Walker constellation would consist of an inclination angle of 70 degrees, one orbital plane, and 6 satellites on that plane, while the solution that imaged all targets, the fastest, was a constellation with the inclination of 70 degrees and 4 planes distributed across the RAN axis and 3 satellites per plane. A 50-target scenario was then evaluated in the same manner. The Pareto frontier was again identified, and the most cost-effective and best-performing solutions are as follows: a 75-degree inclination, 2-plane, and 3 satellites per plane configuration was the most cost-effective of the feasible solutions. The highest performing solution had a 75-degree inclination, 6-plane, and 2 satellites per plane configuration. From this data, the team concluded that a constellation with more satellites scales efficiently to scenarios with a larger number of targets.
Space presents several risks that must be addressed. The European Space Agency estimates there are approximately 170 million pieces of debris in orbit. While the chance of Vector colliding with one of these is low, it is not zero. Additionally, space is home to hazards such as geomagnetic storms, solar radiation storms, radio blackouts, and the potential for adversarial interference. To mitigate these risks, Vector will be constructed from durable, radiation-resistant materials, equipped with a surplus of maneuvering fuel to avoid collisions, and secured with a robust data encryption.
The Vector mission represents the culmination of months of dedication, critical thinking, and collaboration as part of our senior design project. As students, this experience pushed us to apply classroom knowledge to a real-world challenge, fostering both technical expertise and teamwork. Vector represents the cutting edge of what's possible, combining advanced imaging capabilities and optimized designs as well as algorithms to meet critical challenges. As we transition from students to professionals, we hope this work inspires others to push boundaries, tackle complex problems, and pursue innovative solutions that could shape the future of the aerospace industry and beyond.